Welcome to the Raw Coding YouTube channel. My name is Anton, and today I'm going to be talking about dotnet heaps. That's right, multiples of them, not just one. Generally, when C# developers talk about the heap, it is allocating objects into the dotnet heap, and we all know that is bad. What I'm going to be talking about in this video is the details of the heap, how it consists of the small object heap, the large object heap, the generations, and how the objects that you allocate into the heap move across that heap and what impact it will have on your application. You can see the mirror board behind me. We're going to be drawing, so you know it's going to be a spicy episode. Before we begin, I want to let you know I have released my C# programming course, so if you want to learn programming as I do, I highly recommend you go ahead and check it out. Let's go ahead and begin. We're going to be talking about allocating objects on the heap. So we'll draw a region of memory, which is essentially the heap. And what we already know so far, when we type in a new repository or new class, this is going to allocate an object somewhere in the heap. What we're going to try to understand is what kind of objects are we allocating onto the heap, where in the heap it's going to be located, and how that is going to impact the performance or the behavior of your application because of how the garbage collector or how the .NET runtime is going to interact with the heap. So objects don't just get placed randomly somewhere in your memory. The memory that the .NET runtime has grabbed from your operating system and has used for the heap gets split into three main segments: the 0th generation, the 1st generation, and the 2nd generation. Then furthermore, the 2nd generation is split into two parts. On the right hand side of the 2nd generation, and this is not specifically how it's laid out in memory, I don't actually know, I just have a visual representation in my head of how this looks. Things that are located in the large object heap will be things like constant strings, static objects, etc. Things that, don't change. The second important thing to note, if you're creating an object that is bigger than 85 kilobytes, it is going to get allocated into the large object heap. Everything on the left hand side over here, the 0, 1st, and 2nd generation, is referred to as the small object heap. All other objects that you're going to allocate are going to go into the 0th generation. So as the user of the .NET runtime, you're only ever allocating objects into these two regions of memory. And by the way, there are some exceptions to this rule that are not too important. The questions that we have over here in front of us is, well, we have this 1st and 2nd segment. How do objects make it into there? And what's even the significance of having these segments? First of all, let's answer the question of why do we have these segments? When the garbage collection runs, it can choose, do we want to garbage collect the 0th generation? And when it does so, only memory is cleaned up over here. If it chooses to collect the 1st generation, only memory is going to be cleaned up here. If we're collecting the 2nd generation, the whole memory is being checked and cleaned up. And by the way, if you're not aware, only objects that don't have a reference to them get cleaned up. If you have a reference from somewhere on the stack or from somewhere else on the heap, these objects will remain in memory. So the main reason the heap is split into these segments is because it will be cheaper to just clean up this small generation over here rather than the full region of memory. What you want to have is this region of memory being garbage collected as often as possible, and preferably this region in memory not being touched at all. Now that we're armed with this information, we can start asking questions of, well, there is the 2nd and 1st generation. How do things actually get allocated into there? When you're creating objects, so let's say we'll give a little square over here, triangle, right? And there will be references to these two objects, and the references to these two objects have actually been removed. These two objects are eligible for garbage collection. And when the garbage collection is actually going to run, let's say it is running on this 0th generation, and depending on which strategy the garbage collector chooses to run with, either sweep or compact, sweep just takes these objects and flips a bit and says, this memory can now be occupied by something else. Compact will actually do the work to remove the objects and then the rest of the objects, well, compact them together. For now, we're just going to take a look at the sweep strategy. When the garbage collector runs and objects still have references to them, they will get moved on to the next generation. And as you can see, what I've done here is I've taken objects and I've just moved them about. If you want to move objects about like this in memory, that is essentially kind of like compacting, and you have to remove it from one region in memory and place it into the other one. That's not what actually happens. Moving thousands of objects, if you have them over here, to the region in memory over here would be very expensive. What actually happens is this wall just gets dragged over here. Okay, instead of changing many things, we change one thing. And if you have a situation like this, where this object is in this position and this object over here, which has been marked for garbage collection, is over here, so something like this, what's going to happen is this wall will go over here, and now what you have is effectively segmentation. This is where, if the compact strategy would run, this type of object would actually just be removed, and then these two would be placed somewhere over here in this region of memory, right? Everything would be, well, compacted. This wall will be dragged over here, this will be cleaned up, and your memory starts looking something like this. The same thing is going to happen with the second generation. So if garbage collection runs in the first generation and objects with references still survive, they make it to the second generation. Now that we've seen the behavior of these objects in memory, what are we aiming for and what is efficient? All of the objects that you're going to allocate in the 0th generation are either going to be surviving and promoting to the right-hand side into the second generation, or they're going to be garbage collected here, or, you know, when they get promoted to the second generation, they will be garbage collected here. What you don't want to happen is an object that you have allocated here has moved to the first generation and then to the second generation, and as soon as it reached the second generation, whatever reference it had to it, so let's say it had a reference to it, as soon as it makes it to the second generation, it loses the reference. If something like this is happening, that means there is going to be a buildup of objects with no references. And when the garbage collector is taking a look at the 0th generation to garbage collected, what it's actually doing in addition to that is it's just taking a look at these other regions of memory and seeing, okay, what actually has references to it and doesn't, and just takes an account of that. So it may mark something like, does this still have a reference? Does this still not have a reference? And then updates some internal state. So when it comes time to run the garbage collection next time, it can make a decision. I know from previous garbage collection of the 0th generation that there were a lot of objects in the second generation, and now I need to go and collect the whole memory. That is something that you want to avoid. Essentially, the behavior that you're aiming for is allocating all of the objects into the 0th generation, and some of your objects should either be long-lived or they should be short-lived. Where the long-lived objects, once they make it to the second generation, the optimal behavior is they just stay there, and the garbage collector never actually has to go to the second generation and try to garbage collect that memory. Now let's go into Writer and have a little bit of actual visualization around allocating some objects into the 0th generation, into the large object heap, and then seeing objects move from 0th generation across the memory region, and then eventually being garbage collected. What I currently have in my solution is an ASP.NET Core application and some benchmarks. If we take a look at the program.cs, I am registering 2 services, and these are just containers for some data that I'm going to put in there in order to illustrate my points. Then we have 3 endpoints over here, which are interacting with this first service, which is just a collection of long arrays. We are going to allocate a long array of some kind of size and put it inside this bin, and then potentially we also want to be able to clear this bin. When we clear the bin, we are going to release references to all of the arrays that we have created. Please notice that the list itself, because it's a singleton, it's not going to get garbage collected. And then the rest of endpoints, we will get to them a little bit later. The application is currently already running, and if we hit the root, we currently have nothing in there. I'll duplicate this tab so I can interact with it in a different window. I'll go over here, and for the fill endpoint, we are going to fill it up with an object that is 1,000 longs, okay? If I come back over here, you can see, it is quite a few objects. If I take a look at the terminal here, we have allocated essentially 8,000 bytes. what has that actually done to the memory and how can we see it? You can use .memory, which is a JetBrains writer tool, and that's pretty much all I use when I'm looking at the memory of things. So let's take a look at Heaps. And here is essentially the running process. Apologies, it is a little bit slow and might be a little bit hard to see. But let's say I will keep this over here and let's come back to the browser and allocate something that is 5,000 longs. We'll come back over here, we'll see we have allocated 40,000 bytes. And right here where I have allocated this array, you should see just a tiny little bump, okay? It is very minuscule, but I assure you it's there. Maybe I'll do some movie magic to zoom in on it. All of this stuff, if I keep allocating these objects, so I'll refresh this a couple of times, come back over here, we're gonna see everything gets allocated into the 0th generation. Another way to find out if something has been allocated into the 0th generation or whichever other generation, we can take a look at what generation the objects are actually in. So for example, if we take a look at the bin, we will use gc static class to get generation of the current bin. I'll then duplicate this line and the collection that I have generated for these longs, I'm gonna go ahead and print the generation right over here. Let's wait for the application to restart and reattach the profiler. With the profiler now attached, again, I'm gonna come back over here and I'm gonna put on 2 objects. We can see that bins and longs is actually in the 0th generation. If I come back around, I'm gonna go ahead and duplicate this line over here, or this line, this window, I'm gonna clear, and these objects should have been cleared. You will see that the memory hasn't actually reduced. Nothing has happened to the memory. If I force garbage collection, then it's going to get reduced. If I come back over here again and I fill, and we come back, we will see that bin has survived garbage collection, therefore it got moved to the next generation. Long arrays that are being allocated are still allocated in the 0th generation. Now, if we come back and we bump up the numbers over here, let's say we will generate an array with 30,000 elements, and I come back, we are going to see that the big collection that we're allocating is going into the 2nd generation. And this is effectively allocating things into the large object heap. And there is a metric right over here where you can see how much stuff has been allocated into the large object heap since the last garbage collection. And again, just to drive the point home, if we clear again, come back, just because you have removed references to something or something is now null, garbage collection is not going to happen, even when you are allocating new objects. So let's say I'll create a bunch of new arrays. So after spamming that button, we can see the memory is slowly growing and the garbage collection hasn't run. So all of the elements that we have previously cleared are still there in memory. Let's go ahead and force garbage collection, and you can see most of the arrays that we had over there got moved into the 1st generation. Again, if I come back and I clear, I come back over here, and then I force garbage collection again. The 1st generation is actually gonna get cleared away. Now that the bin has survived the 2nd garbage collection, if I refresh, we will see that the bin has now been moved to the 2nd generation. Okay, and that is how it's moving. We can see this process a little bit clearly through this next example of starting, promoting, sweeping, and compacting. And with this force generation example, we're generating 10,000 objects, and this is going to be our collection, which we're gonna add to the bin, but to the object bin, okay? We will then handle the promotion, and when I'm saying promotion, it is being promoted to the next generation. We're gonna allocate one of these objects, we're gonna print the generation for the current bin, and we're going to print the generation for the 1st object that we have allocated in the 1st place. We will then force garbage collection of the 1st generation and then reprint the generations for these objects. This effectively helps us see these objects move across in memory. And then we will remove the 1st element. So the element that we have just moved across to the next generation, the reference to it will be removed. We will then do a sweeping collection. So we will just say collect the 1st generation because that's where the 1st element is now going to be located. And we will see how the bin is going to go ahead and move to the 2nd generation And then we will also perform a compacting collection. So we will start off at this second step over here, skip the sweep and try to do a compact. If you want to do a compact garbage collection, you essentially have to specify a couple of more parameters on the collect method. With these two, you should essentially see the difference. When we're going to sweep, the memory that we're occupying isn't going to change. With the compact, when the memory is being freed, it is actually going to squash the memory. Let me open up Program CS again. These are the 4 endpoints that I'm working with. Let's open up the .NET memory profiler. I'm gonna force garbage collection just to be sure before we start. And let me close this and this. We will start. At this point, we have essentially allocated an object. So right over here in the first generation. And let's open up our logs. We have started. We will then go to promote. So promote. Let's come back. If again we take a look at the methods, right over here, everything was in the 0th generation, now it's in the 1st generation, and we can see it being reflected over here by going from this blue color to this red color, but everything is still staying flat. Let's come back, and now we're going to sweep, okay? Come back over here. You will see that most of the stuff got moved to the 2nd generation, and that's the effect where the border of the 2nd generation just got moved across. And even though we have unreferenced the first element, it is still somewhere there in memory. So that memory is essentially fragmented in the 2nd generation, and at some point compacting is going to run and it's going to squish that memory. Let's go ahead and force garbage collection over here, and we're gonna see that squashing. We're gonna start over by starting. So we're reallocating that array over there. You can see the bump. We're again going to promote, and again it's moved to the 1st generation. And again, remember that when we're promoting, at the end of promotion, we're removing the reference to this object which has just been promoted. When we're going to run compact, so right over here, compact, come back over here, instead of the memory just turning to green and just going to the 2nd generation, there is a slight reduction here. Again, I'm sorry I can't zoom in on this tool, but the array will be gotten rid of, and you can see a bunch of bytes in the console log. And let me actually collapse down the .memory profiler. That is where I have this longer object, and there is actually a deconstructor here. So the deconstructor runs when the object is being garbage collected. Now let's close force gen, and we're gonna come to the obj and list endpoints. So the object allocation right over here, we have some kind of complex object. And what we're trying to understand over here is that most of the times what you and I are working with are just allocating objects, right? So how many objects do you need to allocate into a list in order for it to go over the tipping point so it doesn't go into the large object heap? And this is what this is meant to illustrate. Size of long, the reason we're taking size of long is because the reference is actually a long value. So it's going to be taking up 8 bytes to point to your object. We're then taking the 85 kilobytes, and I'm minusing 3 here after the division. Basically, this is 3 longs that are accounting for something I don't know, like the size of the array, maybe some header of the object. I don't know what this is. Basically, this is somewhere on the border, and it's some allocation that is not specifically the values that you have put into your array. So we have the tipping point, and this size right over here, the tipping point -1, is going to go into the small object heap. And then on this tipping point, when, well, it is the tipping point, it doesn't matter what data you actually put into the object, because remember, this is the tipping point for actually holding references, which are just longs. And this list log is actually going to get allocated into the large object heap. And the tipping point is going to be printed over here, so you can get a rough idea of if you have a collection of so many elements, at which point is it actually going to go into the large object heap. So you can actually account for this situation if you're working with a lot of objects. Let's open up the terminal, come back over here and run the obj endpoint. Come back, you will see that we're allocating 10,622 objects. Please, this is my mistake, ignore the bytes over here. This is not bytes. This is how many references is the exact tipping point not how many bytes this occupies. The bytes over here is completely wrong. So you can see that right below the tipping point, if you have a collection with 10,621 objects, it's going to go into the small object heap. This will get allocated into the 0th generation. As soon as you're past the tipping point, this is going to go into the 2nd generation and into the large object heap. Hopefully I had my profiler running over here and we can see this change happening right over here. Okay, now let's go over to the list handler. The example here is meant to illustrate the tipping point with a list. If you didn't know, a list has an internal array. And when you reach the limit of the internal array, the size of the array gets doubled. So it's not like with the array of objects where we slowly crawled up to the limit. Here you're going to be somewhere close to the limit, and then once your array grows over a certain size, it is just going to double and just smash through the limit. So how do we get to this tipping point? Again, we create the same tipping point calculation, and then we start off with the initial size of the array. We're then looping over and we're doubling the size of array up until we know that while we're doubling, we have passed this original tipping point that we have defined. So we know we're tipping over. We then skip back once, so we know we're going to be somewhere over here before the list gets doubled. We're going to print out where it is exactly that the tipping point is somewhere in the future and where is the current list tipping point. We're going to create this list and we're going to add a range for this list tipping point. So we're going to fill up the list or fill up the internal array of the list. And what I'm getting over here is field get value list. This field that I'm defining over here is essentially getting that internal array of the list. You will see the items array, which is basically that internal array. And if you look for the add method, so right over here, you will see add with resize and then grow. And here is essentially the formula for calculating the doubling of the array, okay? Let's close down the list. So we fill it up to the tipping point, we then get the internal array, and we check the generation for the internal array. I will add one more object to the list, and then the internal array should get dereferenced. A new array will get created, and it will should pass the tipping point because it's getting doubled, and that will get allocated on the large object heap. So not only are you losing a big array on your 0th or whatever generation, you're also allocating another huge array on the large object heap. So this internal array will actually still be pointing to the original array, which is now dereferenced by the list. And we are re-getting the array because this new array will be allocated, and this is going to live on the 2nd generation. So we should see 0, 0, and then 2 right over here. Let's open up the terminal, come back over here. We'll say list, come back, and we'll see right over here that the tipping point, the original one that we previously had as well, is 10,622 elements, but for the list the tipping point is 8,192. Here we can see the internal array is in generation 0 when we push it past the tipping point. Because the original array, again, is dereferenced, then the new one is assigned. This will remain in generation 0, and it's not actually garbage collected. And the new array will get placed in the large object heap. And the size of the array will actually be double of 8,192. So this is essentially the limit that you should be playing with if you're, if you're going to the database and you're saying, I want to get 10,000 objects. Perhaps you should, give it a think and be like, all right, let's get 8,000 objects, not 10,000 objects, because I know that is not going to stress the large object heap as much, okay? If we go to the dotnet memory profiler and maybe slide somewhere over here, we can see this growth in memory where the large object heap is increasing and the heap size in the 0th generation as well. If we force garbage collection, the object in the large object heap should remain, and heap 0 and perhaps heap 2 is going to get compacted, and that is kind of what we see. We go over here. Yep, so that's that. Let's close this down and let's take a look at some benchmarks. I have pre-ran them, so we don't have to sit around and see what have we actually try to run here. So first of all, accessing on small object heap rather than accessing on the large object heap, random access in the small array or random access in the large array, and then you have static access in the small array and static access on the large array. So basically, how expensive is it to read from a small object heap versus the large object heap? And the answer is not that different, okay? And if you're wondering about this computation right over here, the reason I'm doing it is because if you say I want to generate a small subset of random numbers, that is actually going to be more performant if you're going to say I want to generate from a large set of random numbers. Okay, so I'm generating from the same set of numbers and I'm just applying modulo. So the accessing stuff on a small object heap or large object heap is pretty much the same. You can see there is a slight difference over here, but overall we'll say it is pretty much the same. If we try to loop over the heap, so again we're allocating one small, one large, and we're trying to loop over this region in memory over and over. Again, this is kind of like access and traversing the array, whether it's on the small or large object heap, doesn't really matter. The real killer is, hopefully you have guessed, is the allocation. So here I have something to illustrate allocation of different variety of objects on the small object heap. So the calculation is 100 by 60, and this is how many objects we're going to allocate of this size. So if we then take the 0, put it over here, so it's basic multiplication, we're always trying to occupy the same size in terms of the elements that we're storing. And we're always trying to make it up to around 12,000 elements and looping over it 100 times. So if I multiply 4,000 by 3, I'm essentially going to be able to store 12,000 elements, and I'm still looping over them 100 times. I'm trying to see whether it's more efficient to generate objects closer to the large object heap border but less of them, or further away from the large object heap border. However, I'm allocating more objects here. And this is basically sitting somewhere in the middle, where the log, again, we are just creating very big objects, and this is kind of like our baseline. And the results are, they can be surprising or not. Allocating stuff in the large object heap is the most expensive, and again, the exact reason is very hard to articulate. It has to do with the underlying algorithm of the allocator object inside the .NET runtime. For the other results, it looks like you want to allocate bigger arrays and less of them. So reducing the amount of allocations is really the name of the game. And that can mean rolling with a list that is, could be very close to this tipping point that we have defined in this code over here. This will be it for this video. Thank you very much for watching. If you enjoyed it, don't forget to leave a like, subscribe. If you have any questions, go ahead and leave them in the comment section. I have recently released my C# programming course. If you want to know programming as I do it, go ahead and check it out. If you want the source code for this video or my other videos, please come support me on Patreon. Join other amazing people who are helping me bring this work to you. As always, I appreciate your support. Again, thank you for watching. I'll see you later.